Good morning. Let me remind you of what I did in the last lecture. You see, we were discussing the postulates of quantum mechanics, and as I said, there are 4 postulates. The first postulate is here the state of a system is specified as fully as is possible by the state function, which we denote by the symbol capital Psi. And then the state function, once you know it, it is possible for you to calculate the probability that the particle may be found, or your system may be found in a given volume element, which we denote by the symbol d2. The symbol d2 is here. And I also pointed out that depending upon what your system is, the definition of d2 could be different. It may be dx into dy into dz if it is a particle moving in 3 dimensions, while if you idealize the particle as something that is moving in one direction only, then the d2 will be just equal to dx. Now, we will pass on to we discuss the consequences of this. We said that the wave function, in order for it to be acceptable, the function should at least be a square integrable function. And if it is a square integrable function, we can always carry out the process of normalization, which means that I shall multiply the function by a suitable constant in such a fashion that the integral of psi star psi over the entire space is equal to 1, and then we say the function is normalized. In addition to that, we for physical reasons we said we expect the wave function or the state function to be a continuous function of position. And further, we also impose the condition that it should not be a multiple valued function. At any particular point, you should have only a single value for the function. So, now we come to the second postulate. The second postulate is concerned with observables, because you see, I mean, after all, in a lab, what do? We make observations, and therefore, we suppose I make a measurement on a quantum system, what would be the result? So, that is the matter of postulates 2 and 3. So, let me introduce the second postulate, which says that if you have any observable corresponding to that in quantum mechanics, there is a linear Hermitian operator. So, there are several words here in this postulate that needs explanation. First of all, what do I mean by an observable? For our purpose, an observable will be defined by this. We will say that it is anything that depends upon the position and the momentum of the particle. I mean, if I am thinking of a one particle system, it is anything, well, let me say it is one dimensional system. So, it is anything that depends upon x and p, where x is the position of the particle and p is the momentum of the particle. If you have a 3 dimensional system, it may be anything that depends upon x, y, z, px, py, pz. So, that will be my definition of an observable. In fact, the simplest thing is, you see, if I am making an observation, I may be measuring the position of the particle. So, therefore, in that case my observable will be x, or I may be measuring the momentum of the particle, which I shall denote as p. It is probably better to put a subscript x, because this is the momentum associated with the particle due to its motion in the x direction. But you can think of more complex things. For example, you may think of kinetic energy of the particle, and again for a one dimensional system, kinetic energy will be px square divided by 2m. Or if your particle is subject to a potential energy, it is moving in an external field which is caused by a potential we will say okay, there is a potential energy associated with the particle. Potential energy will depend upon the position of the particle. So, potential energy will be a function of x, let us say V of x, and this is yet another example for an observable. You may also say total energy. Total energy is just the sum of kinetic and potential energies. And so, it is going to be Px square by 2m, which is kinetic energy, plus V of x. This is a function of momentum as well as position, and hence is another example for an observable. Then if you look at the postulate, it also says that associated with every observable, each one of these observables, there is a linear Hermitian operator. So, I have to explain what is meant by a linear Hermitian operator. So, let us start with the definition of an operator. I mean, we will adopt a very simplified definition. I mean, if you go to the mathematics department, they will give you more rigorous definitions, but we are not going to do that. We will have a very practical approach. So, the definition or the way in which I am going to define an operator is this. Imagine that I have a function f of x, and I carry out something with this function, maybe multiply it by let us say 4, or maybe differentiate this function, maybe let me say I am thinking of going to differentiate it. So, what do? I carry out the process of differentiation, which we usually denote by the symbol d by dx. And what will be the answer? The answer will be a new function, right, which is the derivative. So, therefore, this gives you a new function, which in this case is nothing but the derivative of the function f of x. So, I will say that okay, what is an operator? Well, if you give me any function f, what I will do is I will perform some operation which I shall denote by this symbol. So, this is an operator. What does it give me? It gives me a new function which I shall denote as g. So, this is my definition of an operator, but then if I write a, see the fact that it is an operator is not conveyed to you. So, therefore, what I will do is I will give it a special hat. So, a with its hat, you should recognize that it is an operator. So, the simplest example for a will be let me say I am going to give you a kind of list which will list different operators. So, d by dx will be let us say a typical operator that I can think of. And let me just for the sake of illustration, let me allow this to operate upon different functions. For example, suppose I have a function like x square, then d by dx operating upon x square, what is the answer? The answer is going to be 2x. So, this is my new function. From x square I have obtained a new function which is 2x. Or I can also think of an operator like taking the square, right, which I shall denote by this symbol. So, what it tells me is that if you give me the function f of x, I will simply take its square. So, that is its operator. So, taking the square is an operator that can be performed on x square. What will be the answer? It is going to be x to the power of 4. You can have other examples, for example, taking the second derivative of the function. Okay, what is going to happen is that if it operated upon x square, the answer will be just 2. Or you can think of let us say multiplying the function by a constant which you may denote, well, let us say the constant is equal to 4. So, if you give me that any function, what I will do is I will simplify, multiply that function by 4 and give you the answer. It is going to be 4x square. Or another simple thing which we will often use is I will take the function, I will simply multiply it by x itself. So, multiplication by x, this is another example. So, I will just denote that by x, and all that I will do is I will, given the function, I will multiply it by x. So, therefore, the answer here is going to be x cube. So, these are all examples of operators, and to make it little bit more clearer, maybe I should think of another function, maybe e to the power of minus x. What is going to happen? Well, let me put a constant also there, maybe e to the power of minus 2x. So, d by dx will give me minus 2 times e to the power of minus 2x, squaring will give me e to the power of minus 4x, taking the second derivative, what will it give me? It will give me 4 times e to the power of minus 2x, multiplication by 4, it is going to give me 4 e to the power of minus 2x, and multiplication by x, what does it give me? It gives me x e to the power of minus 2x. So, it is clear, I mean, what do we mean, what we mean by an operator? You give, what is it? I mean, you give me a function, I will perform some operation, and the result is going to be a new function. Okay. What did I do? Is everything okay? I suppose so. So, therefore, having defined an operator, I should tell you what is meant by a linear operator. So, imagine I have two functions. Imagine I have two functions. The first one I will denote by the simple f, or maybe f1, let me say, and the second function I will denote by the symbol f2. So, these are two functions. For example, one of them may be x square, the other may be e to the power of minus 2x typically. I mean, this may be x square, the other one may be e to the power of minus 2x, and what am I going to do? I am going to add them. So, I mean, they do not have to be these, they may be f1 and f2 may be anything, because we are doing quantum mechanics, we will impose the condition usually that f1 and f2 are acceptable wave functions. Okay. Now, that is what we will do later, but anyway, for the sake of definitions, I mean, the f1 and f2 can be anything, and imagine that I have an operator A acting on the sum of these two, the sum of f1 and f2, and I mean, if I can actually allow A to operate upon f1, and I can also allow A to operate upon f2 separately, right, and if it, and then of course I can sum the two, and if it so happens that A operating upon the sum of f1 and f2 is equal to A operating upon f1 plus A operating upon f2, if this is satisfied for any arbitrary f1 and f2, then I say that A is a linear operator. Okay, but then you say, you may ask a question like this, is it not obvious that this should always be satisfied? And the answer is no, it is not always satisfied. For example, I mean, let us examine this d by dx operating upon f1 plus f2. If you want, you can take this particular example, you can allow d by dx to operate upon x square plus e to the power of minus 2x. What will be the answer? We know what the answer is, because we know how to carry out differentiation of a sum. Differentiation of a sum is, derivative of a sum is equal to derivative of the first term plus the derivative of the second term. So, here it is obvious that it is actually d by dx operating upon upon x square plus d by dx operating upon e to the power of minus 2x, and that is definitely valid irrespective of what f1 and f2 are. So, therefore, in this case it is clear that this must be equal to df1 by dx plus df2 by dx. So, therefore, d by dx definitely is a linear operator. Similarly, if you think of d square upon dx square, that also is a linear operator, because second derivative of a sum is actually equal to the sum of the second derivatives. Multiplication by 4, that is obvious. I mean, if you multiply f1 plus f2 by 4, it is equivalent to multiplying f1 by 4 and f2 by 4 and adding the 2. So, this also is a linear operator. Multiplication by x again is another example for a linear operator, but notice that I did not discuss this one. What about this operator, taking the square? So, as an let us examine whether this is a linear operator. Well, taking the square, you see, you would have f1 plus f2. If this is your sum, you take the square of that is the operation. Now, if that operation is performed on f1, what would be the answer? You will be taking the square of f1, and if you allowed the same operator to operate upon f2, the answer will be f2 square, and then if I summed the two, I am going to get this. Now, the question is whether this is equal to that, and obviously the two are not equal, because when you take the square of f1 plus f2, you will get f1 square plus f2 square plus 2 times f1 f2, and therefore, this is not satisfied, and hence this operator not linear. All the other operators that I have listed here are linear operators. Now, it is easy to think of operators which are not linear. For example, instead of taking the square, suppose you had taken the square root, right. See, square root of f1 plus f2 is not equal to square root of f1 plus square root of f2. So, therefore, this is another example for an operator which is not a linear operator. Or if you like, I mean, you can think of another operation which is taking the exponential. See, for example, if I say that a operating upon f, well, where should I write? Let me define a new operator, a operating upon f. I say, okay, it is equal to e to the power of f. If you give me any function, I will just take the exponential of that function. Very easy to convince yourself that this is not a linear operator, it is an operator that is non-linear. Okay. So, this is enough as far as the linearity is concerned. Now, we have another word sitting here in this postulate which says Hermitian operator. So, what do I mean by Hermitian operator? Okay, let me imagine that I have two acceptable state functions. Let me denote them by the symbol psi and phi. This means, this of course means that you see they can be normalized. So, they are square integrable functions, they are continuous, they are single valued. Now, suppose I allow an operator A to allow an operator A to operate upon the wave function psi or the state function psi, and then what I will do is I will multiply this operator, this result. This of course is a new function. If you allow A to operate upon psi, the answer is a new function. I am going to multiply the result by the complex conjugate of phi. What is the result? It will be something new, some new thing. and what I will do is I will also multiply the whole thing by the volume element d2 and integrate over the entire space. Okay. Now, if you need an example, you see this is written in a general notation. For example, if you say that okay, A is d by dx and psi is a function of x alone, that means that I am thinking of a particle which is moving in one dimension, and this phi is a function of x, and I will take its complex conjugate, and if it is a one dimensional system, what I am really talking about is this integral over the entire space. Over the entire space, it means that I have to integrate from minus infinity to plus infinity. So, if you are thinking of a one dimensional system, this object actually means that. But if you are thinking of a three dimensional system, what is going to happen is that my psi will be a function of x, y, z. Operator A may be perhaps differentiation with respect to x alone, and phi will again be a function of x, y, z. So, this is the special case of a one dimensional system, but this notation as it is written is very general. It can apply to one dimension or three dimension or maybe higher dimensional systems. So, what is going to happen is that once you have performed an integration over the entire space, what is the answer is going to be some number, right. Now, what I can do is instead of doing things in this fashion, I can allow A first to operate upon phi. Right here, notice I am allowing A to operate upon psi, but instead of that, suppose I allow A to operate upon phi, multiply the result by psi star, and then by the volume element d2 and integrate over the entire space. So, what will happen? I shall get some number there, and if it so happens that the number that I obtain here I take it and take its complex conjugate, and if it so happens that after complex conjugation it is equal to this number, then I say that A is a Hermitian operator. Okay, it is a Hermitian operator, not a, I mean, so this is how a Hermitian operator is defined. Now, this definition actually sounds a little bit abstract, and there is a reason why operators that occur in quantum mechanics have to be Hermitian. The reason is that the eigenvalues of Hermitian operators, we will come to eigenvalues in the next postulate, are guaranteed to be real. That is a special property of Hermitian operators. I haven't defined what is meant by eigenvalues, but I will do that. But it is possible to show that if an operator is Hermitian, then all its eigenvalues are real, and as I said, the reason for this postulate will become clearer when I discuss the next postulate. Now, see this postulate actually is saying that if you give me any observable like position or momentum or kinetic energy, there is actually an operator that is associated with this. But the question is, how does one find the operator? The postulate also gives you the prescription for that. So, we continue this postulate. And the second part of this postulate actually gives you a prescription for finding the operator. So, what it says is, if you wanted to find the operator, what you have to do is you have to write the classical mechanical expression for the observable, right. Now, we have actually written down a few observables here, x, px, kinetic energy given by px square by 2m, potential energy given by v of x, total energy given by this expression. So, these are actually classical mechanical expressions for these observables. Classical mechanical expression for position is x, then momentum px, kinetic energy, it is actually given by px square by 2m. So, we have actually done it for a few observables on the board. And then we follow the prescription. What does it say? You look at the expression, you look at the classical mechanical expression, and you have to make these replacements. What are the replacements that the postulate says? If you have x, that is position occurring, then do not do anything. X, the arrow shows x goes to x, that means do not do anything. You do not do anything with position, they remain unchanged, but if you have px occurring in the expression, what you have to do is you have to replace px with minus I h cross dou by dou x. Minus I is actually equal to minus of square root of minus 1, or I is actually square root of minus 1. Okay. And h cross, let me just remind you, I am sure you are all familiar with it, but h cross is equal to h divided by 2 pi, where h is the Planck's constant. So, let us follow this prescription and illustrate the postulate by doing these things, doing those replacements for all these things that are written here. So, here is my classical observable, these are my observables, and what are the associated operators. If you are thinking of x, you do not do anything, so therefore, the operator associated with position for a one dimensional system is just x itself. What does this mean? This means that if you have a function, if you have any wave function or anything, I will just multiply that function by x. That is the meaning of saying that x is the operator associated with position. Similarly, if you say you have momentum, then what you will do is you will have the associated operator, which is going to be minus I h cross dou by dou x. Then if you have kinetic energy, actually kinetic energy is interesting because it has px square. So, if you like, you can say px square is equal to px into px, right, that is what it is anyway, divided by 2m. And then it is clear what we should do. We have 2 px's in this expression. So, we will have 2 minus I h cross dou by dou x, 1 I minus I h cross dou by dou x followed by the other. Okay. So, what this actually means is, you see, if you have any function on which this operator is going to operate, I will allow this operator to operate on it first. That means, if this was operating upon psi of x, if this was operating upon psi of x, the answer will be minus I h cross dou by dou x. That means I am calculating the derivative of psi, but then I have to do the same operation once more. So, that means I will have I would have multiplied, I would have differentiated this once more and then multiplied that by minus I h cross once more. So, effectively what I have is, I have minus I h cross multiplication 2 times, so I am going to get a square of that, and the differentiation I am going to do again 2 times. So, therefore, I would be evaluating the second derivative. So, therefore, let me just remove this because there is not enough space in the table that I am writing. This turns out to be equivalent to taking the second derivative of any function that you have and then multiplying that by minus I h cross the whole square. So, when you take the minus I h cross, actually it is going to be equal to I square h cross square, and I square is minus 1. So, therefore, this is actually going to be minus h cross square, and then of course, I should not forget this 1 by 2m. So, naturally there will be 1 by 2m sitting there. So, this is the operator associated with kinetic energy. And if you think of potential energy again, what is going to happen is, you see V of x, you look at the expression, there is no momentum occurring in this expression, only x is occurring. So, therefore, what do? You do not do anything, because it is just a function of x alone. Then as far as total energy is concerned, things are quite straightforward. Now, after we have seen these examples, you have Px square. So, Px is going to be replaced, Px square is going to be replaced with this object, and Vfx is not going to change. So, therefore, you are going to get minus h cross square divided by 2m dou square upon dou x square plus Vfx as the operator associated with total energy of the system. Now, in our discussions, the operator associated with total energy is very important. It is going to occur in the Schrodinger equation, which I will introduce later, and therefore, it is given a special symbol. It is usually denoted by the symbol H with a hat on top of it to indicate that it is an operator, and it is referred to as the Hamiltonian operator. The reason is that you say in classical mechanics, this object is referred to as the Hamiltonian of the system. P square by 2m plus Vfx is the Hamiltonian, and therefore, this is referred to as the Hamiltonian operator, and it is going to be important. Now, maybe I can illustrate the way things proceed by taking a 3-dimensional system. Imagine you have a helium atom moving in this room. Right? You have a helium atom in this room, something that I talked about yesterday. You say that okay, this room is completely empty except for one helium atom, something that we cannot attain, but it does not matter, as an example to think of. And if you are thinking of, let us say, the total energy of the helium atom, as I said, I am only interested in the helium atom as a particle. I am not going to think of the internal structure. So, therefore, in this room you see the potential energy, there is gravitational potential energy, but we will not worry about that because it is very small for our purpose. So, the helium atom will be executing translational motion, and because of translational motion, what is going to happen is that the total energy of the system will be given by well, its momentum has a component in the x direction, a component in the y direction, as well as a component in the z direction. So, because of its motion in the x direction, the energy will be Px square by 2m, kinetic energy will be so much. Then you will have, of course, Py square by 2m. This is total energy that I am talking about, and then Pz square by 2m. So, this will be the classical mechanical expression for the total energy. The total energy, notice I have taken the potential energy to be 0, right. And this is the kinetic energy. And then what will be the Hamiltonian operator, which will describe my helium atom. Hamiltonian operator is the operator associated with total energy. And what is going to happen? You will make these replacements. You see, you have Px square. So, I am going to get minus h cross square by 2m dou square upon dou x square. Then the next term you have Py square, Py is going to be replaced with minus I h cross dou by dou y. So, you are going to get minus h cross square by 2m dou square upon dou y square. This means partial differentiation with respect to y. Then this is going to be replaced with minus h cross square by 2m dou square upon dou z square. So, this is the operator that is associated with total energy, okay, and it is obvious that this may be written as minus h cross square by 2m dou square upon dou x square plus dou square upon dou y square plus dou square upon dou z square. Now, it is obvious that you see this is rather tedious to write, and therefore, the people have invented clever ways of writing these things. Instead of writing this whole thing, it is usual to write that as del square. So, therefore, the Hamiltonian will be minus h cross square by 2m into del square. So, when you write del square, it actually means this sum of these second derivative operators. Now, suppose for some reason you wanted to include the gravitational potential energy also, you can easily do that. All that will happen is that you will have to say, okay, energy is given by the sum of this plus the potential energy. Gravitational potential energy, as you know, will depend upon the mass of the particle. It will also depend upon g, the acceleration due to gravity, and then of course, it will depend upon the height, right, at which the particle is. So, you can say, okay, the way it is z coordinate measures the height of the particle from, let us say, from the floor. So, therefore, what will happen if that was the way it was, you will say, okay, gravitational energy would be mg z, right. Okay, but as I said, in most of the things, the gravitation is not at all important. Most of our atomic and molecular physics, gravitation does not play any role. I mean, because they essentially because you say we do not cover that much distance in space or that much height in space. But if you wanted to include that, what will happen is that this will be the modification that you will have to do. That is just to illustrate the point. Okay. Now, if I was interested in the internal structure of helium atom, something that I talked about in my previous lectures, then what I will imagine is that I have the nucleus, for example, at the origin, okay, and then I will have the two electrons. I can say, okay, the two electrons will be moving about, and then they will have kinetic energy. They will also have potential energy because of their interaction with the nucleus, because electrons are negatively charged, the nucleus is positively charged. Okay. So, therefore, the expressions will get more complex. We will see such expressions later on in the course. Okay, now, this is the second postulate. What it has said is that if you have any observable, there is an operator, but then you see in the lab what do? We make a measurement, and so we have the next postulate which talks about measurement. So, it says that suppose you make a measurement of a particular observable, then what it says is that the answer will be always an eigenvalue of the corresponding operator. This is the postulate. Okay. To make it clearer, let me consider a specific example. The example will be my hydrogen atom. Remember, in one of my earlier lectures, I spoke about the hydrogen atom, which is adsorbed on the surface of tungsten, and imagine that you displace the hydrogen atom in this direction and release it, then it will execute vibrational motion. So, as far as this system is concerned, what is going to happen is that the total energy, if you assume that it obeys classical mechanics, the total energy will be given by Px square by 2m. This is the kinetic energy, and then you will have to add to that the potential energy of the system. The system has now a potential energy. Why? Because if I take the hydrogen and move it, then what will happen is that this bond which I have shown as a spring will get stretched, right, and the stretching means that you see you are storing potential energy into that bond. So, therefore, you see if you denote the displacement of this atom from its equilibrium position, from here suppose you displace it to a new position by displacing it by an amount x from the equilibrium position. Okay, then what will happen is that the potential energy of the function, sorry, the potential energy of the particle will be dependent upon x. It will depend upon how much you have displaced the particle. So, therefore, you will have V which is a function of x, and the simplest thing is to say that this V is given by a quadratic function of x. So, it is equal to half k x square. This is the simplest model that you can use to describe such a system. This essentially says that if you displace the particle to one side and release it, it will execute harmonic oscillations. It will behave like an oscillator, oscillating with a particular frequency. So, if you say that this harmonic model, we will study this in detail later, but let us say that I will say V of x in this case is very well approximated by a quadratic function of x. Then what will happen is that the total energy will be given by p x square by 2 m plus half k x square, where half k x square is the potential energy of the system, k being a constant, which essentially characterizes how stiff the bond is between the hydrogen and the tungsten surface. So, if you say this is the total energy of the system, then you can ask what is the corresponding operator. The corresponding operator will be denoted by the symbol H. And if I follow the prescription that we saw in the previous postulate, what will happen? This is going to be given by minus h cross square by 2 m dou square upon dou x square plus half k x square. So, this will be the Hamiltonian operator for the system. Now, suppose you look at postulate 3 and ask, suppose I make a measurement of the energy of the system, right. What this postulate says is that the answer is going to be an eigen value of the operator that is associated with energy, and the operator that is associated with energy is the Hamiltonian operator. It is given by this. So, therefore, what it says is that if you make a measurement of the energy of the system, the answer is going to be an eigen value of this Hamiltonian operator. But then of course, I should explain to you what is meant by an eigen value, which I have not done yet. So, let me define what is meant by, let me tell you what is meant by an eigen value. Again, I shall illustrate with this with examples. Let me think of the operator d by dx, and you know that d by dx operating upon maybe x cube gives me the answer 3 x square. Okay. So, what happens is that it operates upon x cube and gives me a totally different new function. But suppose what d by dx does is, suppose I allow it to operate upon a function which I will write as e to the power of I, let me say 3x. So, what is the answer? It is obvious, if you know how to differentiate, you know what the answer is. The answer is just e to the power of I 3x itself, but multiplied by I into 3. right. See, you compare the two cases. In the first case you got a totally new function, but in the second case what is happening is that you do not get a totally new function. What is happening is that you get the original function itself, but multiplied by a constant which is I into 3. Okay. So, therefore, we say that as far as this operator is concerned, this function is special. Why is it special? Because the effect of this operator on this function is just to multiply it by a constant. So, such a function is referred to as an eigen function of the operator. Okay. So, we can generalize this and say, imagine I have an operator A, okay, and suppose when it operates upon a function phi, what happens? I do not get a completely new function, but I get the same function back, but multiplied by a constant, and that constant I shall denote by the symbol small a. So, therefore, a operating upon phi gives me phi back, but multiplied by the constant a. Then I say that this phi is special and it is an eigen function of the operator a, and small a I will refer to as the associated eigenvalue. Okay. So, this is eigen function and small a is the eigenvalue. Now, a given operator may have several different eigen functions. For example, I could have said e to the power of I 4x, right. That also is an eigen function of the operator d by dx. So, e to the power of I 5x again is an eigen function. So, it is possible for a given operator to have a large number of eigen functions, and each eigen function has its own associated eigenvalue, right. In this case, of course, you see the eigenvalue is actually a complex number. In this particular case, the eigenvalue is actually I into 3 or maybe I into 4 or I into 5, depending upon which function you consider, and the eigenvalue happens to be actually a complex number. Strictly speaking, it happens to be a purely imaginary number. Okay. Now, suppose I think of the operator d square upon dx square, and imagine that it operates upon a function which I may denote as sin kx. Well, it is very easy to carry out two differentiations of the sine function. If we carried out two differentiations, what will be the answer? I hope I can just write it as it is. The answer is going to be minus k square sin kx. Well, maybe I can remove this. Okay. So, this makes you realize that sin kx is an eigen function of the operator d square upon dx square, and the associated eigenvalue in this case is minus k square. And it is also obvious that you can have k can have any value, maybe it is 0 or 1 or 1.5, it does not matter what its value is, always sin kx is an eigen function of d square upon dx square. I think I will stop here and continue in the next lecture. Thank you for listening.